resume our lecture. So continuing on from where we left off before the small technical interruption to the Zoom meeting. So when we last left off, we brought up this central idea in predicting precipitation reactions, in that a precipitate must actually form in order for a reaction to be considered a precipitation reaction. So for example, if we mix sodium carbonate and potassium sulfate, and if we try to play a guessing game where we pair each of our cations and anions, in other words, you can think of it as if you're swapping your cations, we'd have potassium carbonate, which is K2CO3, and sodium sulfate. Now, looking at potassium carbonate and sodium sulfate, what state symbol do we assign to these compounds? Are they a solid, liquid, gas, aqueous? Are they soluble or insoluble? What state symbol do we assign to potassium carbonate and sodium sulfate? What state symbol do we assign? Aqueous, yep. So then, if we think about our ionic equation, we notice something that's a little bit interesting. We notice that our reactant and product side of our chemical equation looks exactly identical when you write out your net ionic equation. So then, if we cancel all of our spectator ions, we're left with no reaction. So if all of your chemical species cancel in a chemical reaction, as in if all of your ions and molecules cancel when you try to write the net ionic equation, that's a sign that no reaction has occurred. So you actually have to generate a precipitate for there to be a precipitation reaction. Does that make sense? So let's keep going with this idea, and let's look at the following example where I'd like you to predict the products and write a balanced equation, total ionic and net ionic equation for the following precipitation reaction. And just note the following acids are not strong acids. So let's take about 4 minutes and let's try to predict the products from this precipitation reaction. And remember that you separate each of your compounds into their component ions, you pair your ions, and then from that, you identify the insoluble product, the insoluble ionic compound that you can generate. And we'll discuss this example in about 3 to 4 minutes. And the proposed structure of the precipitate proposed by a student in the chat looks perfect. Don't be shy to message in the chat the proposed chemical formula of your precipitate from this reaction. If you can identify the precipitate, the rest of this precipitation reaction becomes relatively straightforward. And we'll discuss this example in another 2 to 3 minutes. And don't be shy to message me your proposed chemical equation and your proposed formula for the precipitate. And if there are any questions on this example, don't be shy to ask. We'll discuss the first part of this problem in about another minute. Okay, so let's discuss this example. So following our rules for precipitation reactions, we write out each of our component ions. Now this isn't the process for net ionic equations. Like we're just essentially taking all of our compounds and we're breaking them down into ions. Okay? So this is not reflective of what you're doing for the net ionic equation, but it's a valuable tool in terms of predicting the formula of your precipitate. So once we have our ions in place, we swap our cations, okay? And then we list all of the potential compounds that we could form. So we can make zinc sulfide, or we can make nitric acid, HNO3. So now we have to just fill in our state symbols. What is the state symbol for zinc sulfide? What is the state symbol for a metal sulfide? What is the state symbol for a metal sulfide? Solid, yep. Nitric acid. What is the state symbol for nitric acid? Aqueous, okay. So we have our solid, so zinc sulfide is going to be our product. Okay, so we write out our products from our chemical reaction. And now my question to all of you is this equation balanced? Is this equation balanced as written? No, it's not, exactly. So looking at our chemical equation, we have 2 nitrates on the left, we have 1 nitrate on the right. 1 times what? 1 times what would give us 2 nitrate? 2. So we need a coefficient of 2 in front of nitric acid. Okay, so we now have our balanced chemical equation. Now I'd like you to take about 2 to 3 minutes and write a total ionic equation and a net ionic equation for this reaction. And then we'll discuss this example momentarily. So precipitation reactions are, yes, they're also a subclass of reaction known as double replacement or double displacement. That is correct. Mm-hmm. And we'll discuss the net ionic and total ionic equation in about 2 minutes. And the proposed net ionic equation that I see in the chat, it looks reasonable, but make sure to note that when you write out a net ionic equation, you only dissociate your strong acids, strong bases, and soluble ionic compounds. And the proposed total ionic equation that I'm seeing drawn out as a student response looks great so far. Perfect. And the net ionic equation proposed using the annotate feature looks great. So let's now discuss this example and make sure we're comfortable writing out net ionic equations. So zinc nitrate has the aqueous symbol. So we dissociate zinc nitrate into its component ions of zinc 2+ and 2NO3-. Do we dissociate hydrosulfuric acid? Do we dissociate hydrosulfuric acid? Is hydrosulfuric acid a strong acid? No, so we keep it together. It still gets the aqueous symbol. Zinc sulfide we keep together because it's an insoluble ionic compound. And nitric acid, do we dissociate nitric acid? Do we dissociate nitric acid? Yes, it's a strong acid, so that gives us 2H+ aqueous plus 2NO3- aqueous. Okay, now we cancel our spectator ions. Apologies for the minor technical issue. There was a small interruption in the internet connection. I have everything up and running now. Can everyone hear me via Zoom? Is everyone still able to hear me now? Okay, perfect. So we'll continue on. With this lecture. So let's focus on another example where we're asked to predict the products from a precipitation reaction. So in this case, we have the reaction of lead acetate and sodium iodide. I'd like you to predict the product from the following reaction, if there is a product. And then I'd like you to write the total ionic and net ionic equation. and we'll discuss this example. We'll discuss this example in approximately 2 to 3 minutes once we have a reasonable rough outline of our chemical equation. So, don't be shy to message your proposed response for the formula of the precipitate, and then we'll discuss this example in about 2 to 3 minutes. So the main thing you want to be able to do is to predict the product of the precipitate, if any precipitate forms, and fully write the formula of the precipitate. And once you have the precipitate formula established, you can write out the other products from this chemical reaction. And the proposed formula of the precipitate that I see in the chat looks great. Just make sure your formula respects the charge balance, and that you, just like writing the formula of an ionic compound from ions, you cross the charges to get the correct subscript. But what I'm seeing in the chat looks great so far. So since I see a lot of students have the precipitate formula established, let's try to piece it together and propose a balanced chemical equation. And we'll showcase that example in about another minute to a minute and a half. Okay, so let's take a look at this example. So as part of our shortcut, essentially what we're doing is we're swapping our cations. I also like to think about it as we're writing out a pool of possible ions that we can then use to make ionic compounds. Okay, so we have our pool of ions from each of these two ionic compounds. So now we can cross and swap our cations. So we'd have lead paired with iodide. We cross our charges, and that in turn gives us lead iodide. Likewise, if we cross sodium plus and acetate, that in turn gives us sodium acetate. So what would the state symbol be for lead iodide? Is lead iodide soluble or insoluble? Is lead iodide soluble or insoluble? It's insoluble, so it gets a solid symbol. Next, looking at sodium acetate, is sodium acetate soluble or insoluble? Is sodium acetate soluble or insoluble? Soluble, so it gets an aqueous symbol. So we have as our preliminary products, so we have as our preliminary reaction, lead acetate, aqueous, plus sodium iodide, aqueous, leads to lead iodide, solid. plus sodium acetate aqueous. And now my question to all of you is, is this equation balanced as written? Is this equation balanced as written? No, it's not balanced because as we can see, we have 2 iodines on the right. We have 1 iodine on the left. So what times 1 would give us 2 iodine atoms? Okay, so 2, we need a subscript of 2, we need a coefficient of 2. Now as a result of this, we have 1 sodium times 2, that gives us 2 sodiums. So if we have 2 sodiums on the left, and we only have 1 sodium on the right, 1 times what would give us 2 sodiums? What coefficient do we need? What coefficient do we need for sodium acetate? We need 2. Perfect. So now that we have our preliminary balanced chemical equation, we're going to work now on writing out the total ionic and net ionic equation. So first thing we're going to do is we're going to dissociate and separate all of our soluble ionic compounds, strong acids and strong bases. So lead acetate separates into lead 2+, 2 acetate ions. Sodium iodide separates into 2 sodium plus and 2 iodide minus. Lead iodide we keep together because it's a solid insoluble precipitate, and sodium acetate we dissociate into sodium plus and acetate, and we have 2 of them because we have a coefficient of 2. Okay, so now that we have that established, what we're going to do is we're going to cancel all species that are identical on both sides of our chemical equation. And that in turn gives us lead 2+ aqueous plus 2 iodide minus aqueous leads to lead iodide solid. So in most cases, the net ionic equation for a precipitation reaction can be written as the combination of the cation and anion found in your precipitate. Does this example make sense to everyone so far? Does this example make sense to everyone so far? Okay, so let's look at another example. And this time, I'll be guiding you through this example as we're asked to predict the products of a reaction from a word statement. So iron 3 chloride and barium hydroxide are mixed, and we're asked to predict the products. So iron 3 chloride, so we have iron 3+ and Cl-. We cross our charges, and that in turn gives us FeCl3. Barium hydroxide, we have barium 2+ and OH-. We cross our charges, and that gives us BaOH2. Okay, now what is the state symbol for iron 3 chloride? So metal chlorides, are they typically soluble or insoluble? Soluble, so we put an aqueous symbol. Barium hydroxide. So hydroxides in general are insoluble. Is barium one of the few exceptions? So is barium hydroxide soluble or insoluble? Soluble, yep. Barium is one of the few exceptions. Barium hydroxide is soluble. So now what we're going to do is we're going to separate out each of these compounds into their ionic building blocks. And then what we're going to do is we're going to pair our cations and anions and predict the formula of an ionic compound that can be generated from pairing each of these cations and anions. So for example, if we pair iron and hydroxide, that gives us iron 3 hydroxide. We'll figure out the state symbol in a moment. If we pair barium 2+ and chloride, that in turn gives us barium chloride. So what state symbol do we put for iron 3 hydroxide? What state symbol do we put? Is iron 3 hydroxide soluble or insoluble? And I see in the chat the solid symbol. That's exactly right. Iron 3 hydroxide is insoluble. Barium chloride, it's not a very safe compound or solution to drink. It's quite poisonous as it's a pretty soluble form of barium. So it gets the aqueous symbol. Okay. I'm going to put a box around my solid iron 3 hydroxide. That's going to be the precipitate for this reaction. So let's write out our chemical equation. Okay, now that we have our chemical equation set up, this is where the least common multiple method will save you a lot of time. So looking, we have 3 hydroxides on the right, 2 hydroxides on the left. We just move our subscript up to our coefficient. So we put a 2 here and a 3 here. We do the same process for chloride. We swap our subscript into our coefficient. Now, of course, you can do this the longhand way, but the least common multiple method or the cross method is really fast at balancing precipitation reactions. Does everyone understand the logic behind the cross method? Does this look familiar from when we discussed balancing chemical equations? Can I get some feedback in the chat that this looks familiar? Okay, so now that we have our equation, we're going to focus on writing the net ionic equation. So we're going to break down all of our soluble ionic compounds, strong acids and strong bases. So iron 3 chloride breaks down into iron 3+ and 6 chloride ions. Barium hydroxide breaks down into 3 barium 2+ aqueous and 6 OH- aqueous. Iron 3 hydroxide does not break down because it's insoluble. Barium chloride breaks down into 3 barium 2+ aqueous plus 6 Cl- aqueous. Now we cancel our spectator ions. So we cancel chloride. Are there any other spectator ions here? Are there any other spectator ions here? Are there any other spectator ions? What's the other spectator ion in this reaction? Barium, yep, so let's cancel barium. And now in turn, that gives us the following. So if this is our total ionic equation, let's look at our net ionic equation. So we have 2 iron 3+ aqueous plus 6 OH- aqueous leads to 2 iron 3 hydroxide solid. Now, I'm going to ask you a question here. Thinking about our general rules for writing chemical equations, does this equation look correct? Is there something off about this equation? So the equation is balanced, but is there something off about the coefficients? Is there something weird about the coefficients? When we think about chemical reactions, what do we need for our coefficients? Can they be as large as we want, or are there some rules about our coefficients? What does everyone think? Let's try to get some responses in the chat. It must be simplified. We need the smallest possible set of whole number coefficients. That's exactly right. So even though in our total ionic equation, the larger coefficients are acceptable, when you talk about your net ionic equation, you should simplify your coefficients to the smallest possible set of whole numbers. Does that make sense to everyone? Does this example make sense? Are there any questions on this example? If not, let's continue on and let's have you try to apply what you've learned to write out a balanced equation, total ionic and net ionic equation for the following reaction statement. And we'll spend about 3 to 4 minutes getting our initial sketch of our balanced equation and predicting the precipitate generated from this reaction. Our goal is to predict the formula of the precipitate and the products generated from this reaction first and foremost. So don't be shy to message me in the chat or unmute and ask any questions verbally. And I'd like to see in the chat in your responses either your proposed balanced chemical equation or just to get everything started, the proposed formula of your precipitate. So let's spend about 3 to 4 minutes on the first part of this example and we'll discuss shortly. And we already see some perfect formulas of each of our two reactants. And now our job is to assign state symbols to cross our cations and look at what potential new ionic compounds that we can generate. And then in turn, predict the formula of the product from this reaction. So the precipitate is the product. So even if we start with a solid on one side, the precipitate is always on the product side. So try to see if we can generate a precipitate as a result of this reaction. And I would check the solubility rules, as potassium salts are generally quite soluble. So let's keep working through this example and we'll discuss in about another 2 minutes. And the product prediction that I see written using the annotate feature looks good. Now it's just a job of figuring out the state symbols and trying to balance this equation. And I would look over the solubility rules for chromates found in our notes. Think of chromate a lot like sulfate or carbonate. So let's discuss this example now. I'm just going to clear annotations. So first and foremost, magnesium hydroxide. We have magnesium 2 plus, OH minus. We cross our charges. That gives us MgOH2. Potassium chromate. We have K plus and CrO4 for chromate. We cross our charges, that gives us K2CrO4. Okay. Now let's assign state symbols. Magnesium hydroxide, is that soluble or insoluble? Soluble or insoluble? Magnesium hydroxide. Insoluble, so we put a solid symbol. Potassium chromate. Do we put a solid or an aqueous symbol? Is potassium chromate soluble or insoluble? Is potassium chromate soluble or insoluble? It's soluble, so we put an aqueous symbol. Now, to predict the formulas of our product, we're going to try to cross our cations. And we're going to write the formula of the ionic compounds formed by crossing each of our cations with each of our anions. Okay, so let's cross our charges. And that in turn gives us potassium hydroxide and magnesium chromate. So what state symbol do we put for what state symbol do we put for potassium hydroxide? Potassium hydroxide, is that soluble or insoluble? Potassium hydroxide, soluble or insoluble? And don't be shy to type your responses in chat or propose them verbally. Is potassium hydroxide soluble or insoluble? Soluble, yep, so it gets the aqueous symbol. Magnesium chromate, is magnesium chromate soluble or insoluble? Is magnesium chromate soluble or insoluble? Insoluble. Chromate salts, just like most carbonates and hydroxides, are insoluble. So we have our products predicted. We have our product precipitate. So we have magnesium hydroxide solid plus potassium chromate leads to potassium hydroxide aqueous and magnesium chromate solid. Wonderful. Now we have to look at this equation. We see that is this equation balanced? Is this equation balanced as written? Is this equation balanced as written? No, it's not. We have two potassiums on the left. On the left, we have one potassium on the right. 1 times what would give us 2 potassiums? 1 times what would give us 2? 2, yep, perfect. And that's all we need to balance this equation. So now that we have this balanced equation, I'd like everyone to take about 2 to 3 minutes and try to write a net ionic equation for this reaction. So this is an interesting ionic reaction, an interesting precipitation reaction, because it's one of the rare precipitation reactions that is not a double displacement. It's something a little bit different. So let's take about 2 to 3 minutes and propose the net ionic and total ionic equation for this reaction. And then we'll discuss what's so interesting about this reaction. And if you have any questions, don't be shy to message your proposed net ionic and total ionic equation in the chat or using the annotate feature. And I'll provide feedback throughout. And looking at the student responses, the proposed total ionic equation looks perfect. And in the chat, I would double check the net ionic equation. Remember, you only dissociate your soluble ionic compounds, strong acids, and strong bases for your net ionic equation. So the proposed response in the annotate feature looks perfect. Now all we have to do is cancel our spectator ions. And we'll discuss this example and propose the instructor solution in about another minute. But the responses I'm seeing so far look really good. Perfect, perfect. So let's now discuss the solution together as a class. So, first and foremost, magnesium hydroxide, it's insoluble, so we do not dissociate it. Potassium chromate, as it's soluble, we dissociate it into potassium plus and chromate, which is CrO4 2-. Potassium hydroxide is soluble, so we dissociate it into potassium plus and hydroxide. Magnesium chromate is insoluble, so we keep it together. Now, once we have our total ionic equation, we cancel our spectator ions to get the net ionic equation. So potassium gets canceled, and we're left with the following equation. So magnesium hydroxide solid plus chromate leads to magnesium chromate solid plus hydroxide. So this is known not as a double exchange, but instead a single displacement, where chromate displaces hydroxide from the compound. So precipitation reactions are overwhelmingly exchange reactions, but I wanted to show you an example of a precipitation reaction that is a displacement reaction. Does this example make sense to everyone? Is everyone feeling quite, oh, there should be a 2 here. There we go. Is everyone comfortable with this example? Any questions on writing net ionic equations and predicting precipitation reactions? Okay, so let's keep moving on and let's discuss the next major class of reaction, which are neutralization and acid-base reactions. So a neutralization and acid-base reaction involves the reaction of an acid with a base. Whoops, that's the wrong pen. Now, the key feature of an acid-base reaction is the transfer of H+, otherwise known as a proton, from the acid to the base. Okay, just as a refresher, we like to view acids as H+ donors and the base as an H+ acceptor. So for example, in the reaction between oxalic acid and sodium hydroxide, we observe the transfer of H+ from oxalic acid to sodium hydroxide. So the acid loses a proton, the base gains a proton. Another example of an acid-base reaction, would be, for example, hydrochloric acid reacting with lithium hydroxide to yield lithium chloride and water. Another way that you can think about acid-base reactions is they're almost like an exchange reaction where we exchange H+ and the metal cation. And in turn, we get two new compounds. However you prefer to think about acid-base reactions. Now, in an acid-base reaction, the acid donates a proton, it gives H+, loses H+, and that in turn generates what is known as the conjugate base. So the acid and conjugate base are related by H+. Further, the base accepts a proton, the base gains H+, and that in turn generates what is known as the conjugate acid. So fundamentally, acid-base reactions are based on the transfer of H+, the transfer of a proton from the acid to the base. Okay, so let's now discuss other types of acid-base reactions. So strong acids donate H+ to strong bases to form water and a salt. So let's give an example of a strong acid. Would someone like to in the chat provide an example of a strong acid? What strong acid do we want to talk about? What's an example of a strong acid? HCl, sure. So we have hydrochloric acid. And for our strong base, let's do barium hydroxide. Okay, so there's a transfer of a proton from our acid to our base in order to generate water and a salt. where our salt would be barium chloride. Now, one thing that's very useful to balance acid-base reactions is to think about acid-base reactions in terms of H plus equivalent. So I have one H plus equivalent in HCl, and I have two OH equivalents in barium hydroxide. So I need to add a coefficient of 2 to HCl so that we have two H plus equivalents, two OH equivalents, which yield two water equivalents. You can also use the formula of the salt. If you're able to effectively predict the salt, which contains your cation and your conjugate base, it gives you a lot of leverage in terms of balancing the chemical equation. Whatever method you prefer to use, both are valid. Okay, let's look at the next example. So strong acids will donate H+. So what's another example of a strong acid besides hydrochloric? What's an example of a strong acid besides hydrochloric? What's another example of a strong acid? Sure, perchloric acid, okay. So perchloric acid, aqueous, a strong acid, will react with a weak base, such as, for example, ammonia. And that in turn generates a weak acid, where our weak acid is something like ammonium. And as a byproduct, we also generate a conjugate base, such as chlorate. Okay, so strong acids react with weak bases to yield a weak acid. Now, what about weak acids? So let's suppose you have a weak acid. What would an example of a weak acid be? What would an example of a weak acid be? What's an example of a weak acid? Sure, hydrosulfuric. So we have H2S aqueous. So this weak acid will react with a strong base, such as, for example, sodium hydroxide aqueous. And in turn, it will generate a weak base. In this case, for hydroxide, our weak base is the conjugate base of hydrosulfuric acid, which is sulfide aqueous. And we'd also generate as a byproduct water. Again, acid-base reactions are characterized by the transfer of a proton, by the transfer of H+ from our acid to our base. Do these examples make sense so far to everyone? So these are the different types of acid-base reactions. The final type of acid-base reaction is that between a weak acid and a weak base. This reaction is reversible, and these reversible reactions that are occurring at equal rates is known as an equilibrium. To answer the question, what is the weak base? In this case, the sulfide product is our weak base. So we go from a weak acid to a weak base. Did that answer your question? Did that address your question? Perfect. Now, when you have a reaction between a weak acid and weak base, and you'll see these a lot in general chemistry too, these reactions are reversible, and we designate these reversible reactions at equilibrium with these back and forth arrows. We won't see a lot of these equilibrium reactions in general chemistry 1, but they show up a lot in general chemistry 2. Okay, let's keep going and let's talk about acid-base reactions in relation to other types of chemical reactions. So acid-base reactions can generate gas phase products. And a gas-forming reaction, as its creative name implies, is a reaction that generates a gaseous product. So for example, if you take ammonium chloride aqueous and you treat it with sodium hydroxide, you will generate, in turn, ammonia, which is a gas, water, and sodium chloride. In fact, one way that you can detect the presence of ammonium in a salt is by treating it with base and observing the resulting generation of ammonia, which has a very distinct smell. Other types of reactions that are interlinked with acid-base reactions are known as decomposition reactions. So some acids and bases undergo decomposition that generates gas. We've actually seen an example of this already when we looked at the molar volume of carbon dioxide. So in a decomposition reaction, a compound will react to give one or more elements or compounds. So the most common examples of decomposition would be reactions that make carbonic acid, which is H2CO3, or reactions that make sulfurous acid, which is H2SO3. Other gases that you should be aware of are hydrogen sulfide and ammonia, both of which smell terrible. So we can give an example of a reaction that makes hydrogen sulfide. So if you take, for example, sodium sulfide aqueous and you treat it with sulfuric acid, you will generate hydrogen sulfide. Notice how when I'm talking about hydrogen sulfide, I'm using the nomenclature for the gas phase compound. And as a byproduct, we generate sodium sulfate. So this you can smell. And this is actually part of some of the analytical tests for sulfide salts. It'll be harder not to notice if you have a sulfide salt in an acidic solution. So to talk about some other decomposition reactions, carbonic acid decomposes to yield carbon dioxide gas and water. So for example, if you take hydrochloric acid and you react it with sodium carbonate, you will generate carbonic acid in solution. You'll generate carbonic acid. But the carbonic acid doesn't actually stick around very long. It decomposes to yield carbon dioxide and water. When you run a classic baking soda and vinegar reaction, or if you put any carbonate in acidic solution, you'll see bubbles. And the source of these bubbles are the generated gaseous molecules of carbon dioxide. So these are the bubbles that you observe in many reactions of carbonates with acid. Just to round out, we'd also get as a byproduct sodium chloride. So this is how we have acid-base reactions interlinked with decomposition reactions. Another example of a decomposition reaction is that sulfurous acid, H2SO3, decomposes to yield sulfur dioxide gas and water. And in fact, the distinct smell of sulfur dioxide allows you to detect sulfite salts via treatment with acid. So for example, if you have 2 hydrobromic acid reacting with potassium sulfite, you will generate in solution sulfurous acid, which decomposes to yield water, sulfur dioxide gas, and 2 molecules of potassium bromide. Does this make sense how acid-base reactions can sometimes be combined with decomposition reactions? Does everyone understand how these reactions function? And does everyone get the key feature of an acid-base reaction, which is the transfer of a proton? Is everyone comfortable with this idea so far? Any questions? Okay, so let's discuss the following example. I'd like you to predict the products of the following reaction. Hint, maybe try to think, do I have an acid or base in this reaction? And then I'd like you to try to write a balanced chemical equation, total ionic equation, and net ionic equation for this reaction. Now, I'm going to guide you through this first example. So we know hydrochloric acid is our acid. And my question to you is, what state symbol do I put for hydrochloric acid? And we've been doing this a lot, so this one should be pretty familiar to everyone. What state symbol do we put? Aqueous, okay. Aluminum sulfide, what state symbol do we put for a sulfide salt? Are they soluble or insoluble? Are sulfide salts soluble or insoluble? Insoluble, so we put a solid symbol. Okay, perfect. Now, I'm going to show you a trick for acid-base reactions. Remember I said that acid-base reactions are a lot like fancy exchange reactions? So just try, just like for precipitation, swap your cation and H+. And let's try to see what compound formulas we can get. So we have aluminum 3+ and chloride. If we cross our charges, that gives us aluminum chloride. We have H+ and sulfide. If we cross our charges, that gives us hydrogen sulfide. And immediately I think to myself, okay, this reaction is going to generate a gaseous product. What state symbol do we put for aluminum chloride? What state symbol do we put for aluminum chloride? What state symbol do we put? Aqueous. Okay, perfect. Okay, so now that we have this proposed product scheme, let's write out our chemical reaction. And now let's try to balance our chemical equation. So in effect, what has happened in this acid-base reaction is that we have donated H+ from hydrochloric acid to sulfide. So if we want to balance this equation in the traditional sense, we can look and we can count our atoms. We see that we have 2 aluminum on the left. We have 1 aluminum on the right. 1 times what would give us 2 aluminum? 1 times what would give us 2? What coefficient do we need for aluminum chloride? What coefficient do we need? 2, okay. So that gives us 6 chlorines. We have 1 chlorine and 1 hydrogen on the left. 1 times what would give us 6 chlorines? What coefficient do we need for hydrochloric acid? 6, yep. So now we have 6 chlorines and 6 hydrogens. We have 6 hydrogens on the left. Actually, let's look at sulfur since it's easier to count. We have 3 sulfurs on the left. We have 1 sulfur on the right. 1 times what would give us 3 sulfur? What coefficient do we need for hydrogen sulfide? 3, yeah. Okay, so that's the traditional method. I'm going to now show you the shortcut method. So we have 3 sulfides, okay? So to balance out our 3 sulfides, let me use blue color since sulfide is our base. So to balance out our sulfides, we need H+. And if we cross our charges, we see we need 2 hydrogens per sulfide. So if we have 3 sulfides, we take 3 sulfide times 2 and get 6 hydrogens. This is the other method of balancing. Acid-base reactions, and it's counting proton equivalents. Whatever method works for you, you're welcome to use. Now that we have this acid-base reaction established, we're going to write out our total ionic equation. So we're going to dissociate all of our soluble ionic compounds and strong acids. Do I dissociate aluminum sulfide? Do I dissociate aluminum sulfide? Do I break aluminum sulfide apart or do I keep it together? No, we keep it together. It's insoluble. Okay, aluminum chloride, we break apart into 2 aluminum 3+ aqueous and 6 Cl- aqueous. Do we break up hydrogen sulfide? Do we break up hydrogen sulfide? No. Okay, now we cancel our spectator ions, which are chloride, and we're left with the following reaction. And here you can pretty clearly see for our net ionic equation that there is a transfer of a proton, which in turn leads to the generation of a gas product. Does this make sense to everyone so far? Any questions so far? Okay, so let's try to look at the following reaction. This is likely going to be an acid-base reaction. You can tell by the presence of a base, the hydroxide salt, and the presence of an acid in the form of ammonium. So let's try to predict the products of this reaction, and let's try to write a balanced chemical equation, total ionic and net ionic equation. And we'll discuss the first part of this example, which is just predicting the products of this reaction, in about 3 minutes. And the assigned state symbols I see, as well as the products predicted, look correct so far. But I would break up ammonium hydroxide into ammonia and water. The way you have it written is technically perfectly correct. But I'm just trying to show the fact that this reaction will likely generate a gas as well. But the proposed products that I see so far look perfect. So let's discuss this example. I'm going to clear it and then we can discuss. But the responses I saw looked perfect. So again, one quick trick is you swap and exchange your cations. Another way that you can think about acid-base reactions is you're just swapping your cations or swapping H plus with your cation. So that in turn gives us ammonia crossed with hydroxide, which gives us ammonium hydroxide. Now you can write this out as ammonium hydroxide with no issues, but ammonium hydroxide is really equivalent to ammonia and water. So ammonium hydroxide, you commonly see it on the label for ammonia bottles in water, and it's another way of saying ammonia dissolved in water. Both are fine. Both I would accept on an exam. Okay, let's look at our other product. We take silver plus, Cl minus, we cross our charges, and we get silver chloride. What would the state symbol be for silver chloride? What would the state symbol be for silver chloride? Solid. Okay. So now punching this into our equation. So we have ammonium chloride, which is soluble. Ammonium and chloride salts are soluble. Let's look at silver hydroxide. Is silver hydroxide soluble or insoluble? Are hydroxide salts generally soluble or insoluble? Insoluble. So we put a solid symbol. Okay, and then we write out our products of ammonia gas, water, and silver chloride solid. And the total ionic and net ionic equation for this reaction doesn't look too bad. So we can do this together as a group really quickly. So we dissociate all of our soluble ionic compounds, strong acids and strong bases. Ammonium chloride dissociates into ammonium plus chloride. Silver hydroxide we keep together. Now, let's wait a moment, and we missed a really important step that I just want us to check. Now, I blazed ahead because I could see that this equation is balanced, but I just want us to check mentally for a moment. Is this equation balanced as written? Is this equation balanced? Is this equation balanced? Before we move on, you always want to check that. Okay, it's balanced, so I'm going to put a check mark. Okay, so I can keep going with writing out my total ionic equation. Okay. So we've dissociated all of our soluble ionic compounds, strong acids and strong bases, and this is our total ionic equation. The net ionic equation, since there are no spectator ions, it's identical. Our net ionic equation just looks exactly the same as our total ionic equation. Perfect. So here is our total and net ionic equations. They look identical in this case. Does this example make sense to everyone so far? Any questions so far on this example?
So for future reference, so H2O never breaks down, right? It's just always going to stay liquid no matter what.
You only dissociate your soluble ionic compounds, strong acids, and strong bases. Molecular compounds you keep together. Water we just always keep water together. What was that?
Your connection was cutting out.
Oh, so even though technically water does dissociate a very small amount in solution, we're writing always keep compounds together.
Yeah, your connection cut out again.
Okay, one moment. Let me just check one thing. I'm just going to double check and try to modify my connection. Is everyone able to hear me? Okay, that works. Oh, okay. So just to check, is everyone able to hear me now?
Yeah, you sound good.
Okay, perfect. Sorry about that. The power is out in the area, so I'm using a hotspot to stream this Zoom meeting. Okay, so to address the question with regards to whether we dissociate water. So water technically does dissociate slightly in solution, but when writing net ionic equations, we always keep our molecular compounds, weak acids, and weak bases together. We do not dissociate them. So water will always stay as a molecular compound. Did that address your question?
Yes, thank you.
Perfect. And if there are any audio issues, don't be shy to let me know and I'll be happy to correct them. So let's do an example now where we try to predict the products of an acid-base reaction, this time given a word expression. So we're mixing sodium phosphate and sulfuric acid. So let's do this example together. Sodium phosphate, we have sodium plus aqueous, and phosphate, which is PO4 3-. we cross our charges, and that in turn gives us Na3PO4 aqueous. Sulfuric acid, so for sulfuric acid, we have H plus and SO4 2 minus. We cross our charges, that gives us H2SO4 aqueous. Okay, now in terms of predicting products, what we do, acid-base reactions are just fancy exchange reactions. So we swap our cation and H plus. So we have H plus and phosphate, which is PO4 3 minus. If we cross our charges, that gives us H3PO4, which is phosphoric acid. For our other compound, we have sodium plus and sulfate. We cross our charges, that gives us Na2SO4 aqueous. Okay, so now that we have our two product formulas established, we write out our product formulas. So we have Na3PO4 aqueous plus H2SO4 aqueous leads to H3PO4 aqueous plus sodium sulfate, which is Na2SO4 aqueous. Now we have to ask ourselves before we get too over eager, is this equation balanced? Is this equation balanced? Is this equation balanced as written? No, it's not. So let's check why that is. Let's check how can we balance it then. So the fastest method I like to use is the least common multiple method, otherwise known as the cross method. So we put a 2 and a 3 because we take our subscript and we cross it into the coefficient of the opposite compound containing that ion. The cross method is wonderful for balancing exchange reactions. Let's continue crossing our, let's continue to cross our subscripts to our coefficient, and that in turn gives us the following balanced chemical equation. So now that we have the following chemical equation, we're going to focus now on writing out a total ionic and net ionic equation for this reaction. So the first thing that I want to ask of all of you, do we dissociate sodium phosphate? Looking at the state symbol, if we wanted to write a total ionic equation, do we dissociate sodium phosphate? Is sodium phosphate soluble or insoluble in water? Is sodium phosphate, it's soluble, right? So we write this as, so we can dissociate sodium phosphate into 6 sodium plus aqueous plus 2 phosphate. Do we dissociate sulfuric acid? Is sulfuric acid a strong acid or a weak acid? Do we dissociate sulfuric acid? Yes, it's a strong acid, so we dissociate into 6H plus aqueous plus 3SO4 2 minus aqueous. Do we dissociate phosphoric acid? Do we dissociate phosphoric acid? No, phosphoric acid is weak, so we keep it together. And do we dissociate sodium sulfate? Do we dissociate sodium sulfate? Yes, so that breaks down into 6 sodium plus aqueous plus 3 SO4 2 minus aqueous. And now my question is, do we have any spectator ions? What are our spectator ions in this case? Sodium, yep, so let's cancel sodium. What else?
Sulfate?
Yep, exactly right. So we cancel sulfate, and that gives us the following net ionic equation. So that gives us 2 phosphate plus 6H plus leads to 2 phosphoric acid aqueous. And my question to all of you is, can we simplify this equation? Is there a simpler way to write this equation? Yes, so we can write it as by canceling and simplifying our coefficients as 1 phosphate reacts with 3H plus to yield phosphoric acid. So we can really see this acid-base reaction in action where you have a transfer of a proton to your basic phosphate. Does this make sense to everyone so far? Does this make sense to everyone so far?
Hey, Professor, I had a question.
Yes, please go ahead.
For the 6H plus, would
Yes.
it still be right if I put 3H2?
So in this case, make sure that your ion formula matches the actual ions in solution. So for example, like H2 plus is an entirely different species than 2H plus. So always make sure that when you're breaking down your strong acids and ionic compounds, you multiply the subscript by the coefficient and you put it in front of the formula of your ion.
Okay.
Does that make sense?
Yeah.
Perfect. So let's keep going through, and now this time I'm going to ask you, as I've demonstrated an example of this already, I'd like you now to take a look at the following word chemical equation, and I'd like you to try to predict the products of this reaction. This is about as difficult as these kinds of prediction problems are going to get. So let's spend about 3 to 4 minutes trying to predict the products as well of this reaction. And then we'll come together to discuss in about 3 to 4 minutes. And then we'll break off again for another 2 to 3 minutes to try to write out the net and total ionic equations. But first, try to use what you know about acid-base reactions to try to predict the products. And I'd like you to pay special attention to carbonates. Remember, when I think carbonate, I usually think bubbles because they really love to generate gas when they react with acid. And your job is to figure out what gas are we generating. So we'll discuss this example in about 3 to 4 minutes. And if you have any questions or if you have any proposed solutions, don't be shy to share them in the chat using the annotate feature or unmuting and asking your question or sharing your perspective verbally. and we'll discuss this example in another 2 to 3 minutes. I'd like to see a few responses either in the chat or using the annotate feature on the proposed products from this reaction. Yep, the formulas look good. And I see the formula of carbonic acid. And one thing I'd like us all to think about is this looks great so far, but I'd like you to think about what happens to carbonic acid. Is there something special about carbonic acid? Does it break apart into something? So carbonic acid is not very stable, so it decomposes into what two molecules? So take a moment to think about that, and we'll discuss in about another minute. And if anyone in the class would want to chime in, oh wow, we already have it proposed. Yes, carbonic acid breaks down into water and carbon dioxide. Okay, so let's now discuss this example. This has been wonderful so far. Thank you all for participating and sharing your perspective. So for lead carbonate, we have lead 2+, carbonate is CO3 2-. We cross our charges, that gives us PbCO3. We add it to sulfuric acid, which is H+, and SO4 2-. The reason why I like doing this charge crossing approach to writing the formulas is because it gives me a nice little guidebook when I want to go and try to write ionic equations. Now, as our trick for writing out the formulas of acid-base reaction products, we exchange our cation and H+. That gives us H+ and CO3 2-. We cross our charges. That gives us H2CO3 aqueous. We take lead 2+, we cross it with SO4 2-. We cross our charges. That gives us lead sulfate. And what is the state symbol for lead sulfate? Is lead sulfate soluble or insoluble? It's insoluble, so we give it a solid symbol. Okay, so now we write out the formulas. So lead carbonate, just to fill it in, is lead carbonate soluble or insoluble? Lead salts and carbonate salt, so they typically soluble or insoluble? Insoluble, so we put a solid symbol. Sulfuric acid, as it's an acid, is clearly water soluble. Carbonic acid, we'll talk about that in a second. We'll write out lead sulfate for now. And carbonic acid, it's one thing to keep in mind that carbonic acid in solution is not stable. So it will break down into water and carbon dioxide gas. This is why, for example, when you mix calcium carbonate with acetic acid, so your classic baking soda and vinegar reaction, you observe bubbles and a large amount of carbon dioxide. Now, before we move on, I'd like you to take a look at this equation and I'd like you to check, put a little checkbox next to it. Is this equation balanced? Is this equation balanced? Is this equation balanced? Oh, okay, I didn't see the check mark there. Okay, perfect. Yes, this equation is completely balanced. I always want you to think about that because That's often how standardized exams and how students get tripped up on exams. They write out the equation, they don't balance it, and then they're in a weird spot. Okay, so now let's write our total ionic equation. So we don't dissociate lead carbonate, it's insoluble. We do dissociate sulfuric acid as it is water soluble. Lead sulfate, we do not dissociate, it's insoluble. And water and carbon dioxide, just like we discussed, we keep them together as their molecular compounds. So the total equation and the net ionic equation are identical. Is everyone comfortable with this example? Is everyone comfortable with this example? Any questions? Okay, so let's keep going now. So in this next section, we're going to introduce the idea of redox reactions. And what we're going to do, as redox reactions are a large subsection, we're going to pause the lecture here and continue on with our lecture tomorrow. And we'll take a moment and we'll get set up to discuss today's laboratory, which is quite a fun one on electron configurations. So I'm going to pause and stop this lecture recording, and we'll move our discussion now to the laboratory experiment today.